Hello everyone, welcome to another lesson in Theory of Structure. I am Engineer J and we have this new topic here. We have influence line for beam. So before anything else, what is influence line and what is the purpose of influence line? So the objective of the study is we draw the influence line for beam and trusses and understand the application of influence line. So influence line, by the way, this represents the variation of either the reaction, shear, moment, or deflection at a specific point in a member as a concentrated force moves over the member. So in the case, like for example, if we have a moving loads, passing through a bridge, like for example, if this is our load, so as our load P moves from, let's say, from A to B, our reaction forces also changes. As our load P is moving from A to B, our reactions are changing as well. And these are AY and BY. And to define how our reaction changes, so we draw an influence line to determine where is the location of P that would give us the highest value of AY or the highest value of BY. So that's the purpose of influence line. So influence line is used to observe the behavior of our reactions as our load is moving across the beam. Again, as our load P is moving, there's also a changes in the reactions in the moment or deflection at any specific point in our beam. And influence line is used to determine at where should the load P be placed in order to determine the highest moment, in order to determine the maximum shear and the maximum deflection of that specific point in the beam. So that's the purpose of influence line. And we have a two approach in computing for or in drawing the influence line. So by using statics, so by applying equilibrium equations, and we also have the easiest and the fastest one. We have the by Muller-Breslau's principle. So this is to expedite the process of drawing the influence line of our beam. Now, the procedure of how to draw the influence line will be discussed to you in the following examples. So we have this first example here. So this is our beam, and we are asked to draw the influence line for letter A, the vertical reactions at support A and C, and the shear just to the right of support C, and the bending moment at point B of the beam. So we are asked to solve these three questions using one, by statics or by equilibrium equations, and number two, the Muller-Breslau's theorem or principle. So again, this is our beam. So let's say this is a bridge, and we are asked to determine the behavior of our reaction at A as our load or live load is moving from A to E. Let's proceed now to drawing of the influence line. So our first question is the influence line for the vertical reactions at support A and C. So we are asked to determine or to draw two influence line for these 2 points. So our first procedure here is by doing statics or by using statics equation. In creating an influence line, we need to put a live load on every points or in every specific points in our beam. And we begin on the left side of our beam. So the first step here is to put a live load at x is equal to 0. So we put our live load at point A. So we have 1 unit load at that point. So we compute for all the reactions at A, C, and E. So we have AY, CY, and EY. Okay, so in that case, we can compute EY first here by cutting at the internal hinge, so at D. So when we cut at that point, we have these internal forces, and as we all know that if this is an internal hinge, we have no moment at point D. So in this case, we can sum up moment at D, and we know that the distance is 4 meters. So we have summation of moment at D is equal to 0, counterclockwise positive. However, take note, we do not have external forces on the right side of our D, so therefore we can say directly that EY is equal to 0. So we have EY here is equal to 0. And then we compute for the value of C by summing up moment at A is equal to 0, counterclockwise positive. So we have here EY, then the moment arm is 12, that is from A to E, plus CY times 4, and we do not have external loads on the beam which has a moment at point A, so we can directly say that this equation is equal to 0. However, we know that E here is 0, so we can cancel this out, and we can conclude that CY is also 0 here. So therefore, CY is equal to 0. And to compute for A, we can just sum up a force vertically, and this equals to 0. So all the force acting upward are positive. So we have AY plus CY plus EY minus 1 is equal to 0. But take note, CY and EY here are all 0. So therefore, AY is equal to 1. So AY here is equal to 1. Since our first influence diagram here refers to the reaction at A, so therefore when our x is equal to 0, we can say that AY is equal to 1. So later on, we will plot this on our influence diagram. Then we move our 1 unit load on the second point. Okay, we can go directly to point C, so that is x is equal to 4. So we place our 1 unit load at point C. So we put our 1 unit load here. So we have 1. Then we compute for the reactions AY, CY, and EY. So the same strategy we cut at D, but since we do not have load on the right side of D, then we can say directly that EY is equal to 0. So after this one, we sum up moment at A is equal to 0, counterclockwise positive. So we have here EY times 12 plus CY times 4 minus 1 times 4. This is equal to 0. But EY is equal to 0, so therefore we have CY equals to 1. But since our goal here is to compute for AY, that is our first question, so we sum up forces vertical is equal to 0, upward are positive, then we have AY plus CY plus EY minus 1 is equal to 0. But we know that EY here is 0 and CY is 1, so we have AY plus 1 minus 1 is equal to 0. Then AY is equal to 0. So that means when our x is equal to 4, or when our unit load is at point C, our AY value is 0. And then we move our 1 unit load at point D. Okay, so when our x is equal to 8, and then we compute for the reactions AY, CY, and EY. So the same procedure, we cut at D, but when we cut at D, we do not have external load that could give us a moment at D. So therefore, we can directly say that EY is equal to 0. Again, if we cut at D, so we would have this one, this is our DY, and this is our DX, and this our 1 unit load is at point D, and this is our EY. So take note again, if we sum up moment at D is equal to 0, counterclockwise positive, so we have EY times 4 is equal to 0. So automatically, EY here is 0. And then we compute for C here by summing up moment at A is equal to 0, counterclockwise positive. So we have here EY times 12 minus 1 times 8 plus cy times 4 is equal to 0. We have ey is 0 here, so the remaining would be negative 8 plus 4 cy is equal to 0. That means we have cy is equal to 2, correct? But we compute for ay here by summing up forces. Vertical is equal to 0, upward force are positive, so we have ay plus cy plus ey minus 1 is equal to 0. So we have ay here plus 2 plus 0 minus 1 is equal to 0. So therefore ay is equal to negative 1. So therefore when x is equal to 8, ay here is automatically equal to negative 1. Okay? Now for our last condition, we place our 1 unit load at point E, or when our x is equal to 12. That is the location or the distance from E to A. So in this case, we can again cut at point D. So we have here the reaction at EY, the internal forces at D, so dy and dx, and we have the external load, 1 unit load at support E, and we know that the distance is 4. So if we sum up moment at D is equal to 0, counterclockwise positive, this would give us ey times 4 minus 1 times 4 is equal to 0. We have ey is equal to 1. Okay, so we have the value at ey, which is equal to 1. But since we need the value of A and C, because that has been asked according to the problem, so we can just sum up moment at A is equal to 0, counterclockwise positive. So we have ey times 12 minus 1 times 12 plus cy times 4 is equal to 0, and ey here is 1. So we have 1 times 12 minus 12 plus 4 cy is equal to 0. But since 12 minus 12 is equal to 0, so the remaining here would be cy is equal to 0. Okay? So we have cy is equal to 0. And we need also the value of ay, so we can sum up forces vertical is equal to 0. Upward are positive, so we have ay plus cy, then plus ey minus 1 is equal to 0. So that means we have ay plus 0 plus 1 minus 1 is equal to 0. So we have ay also equals to 0. So we have ay is equal to 0. So that means when our x is equal to 12, then ay is equal to 0. So the next thing we do here is to plot the value of our ay with respect to the value of our x. So if we try to tabulate the value when x equal to 0, we computed that the value of ay is equal to 1, correct? So that means when x equal to 0 at this point, so the value of y is 1. So we have a 1 here. Now for our x is equal to 4, the value of ay is equal to 0. So therefore at x equal to 4, the coordinate of our influence line here is 0. Now when x is equal to 8, our ay here is equal to 1. Okay? So when x equal to 8, so at this point, our ay here is equal to negative 1. So therefore at this point, our ay is negative 1. So we have here negative 1. And lastly, when our x is equal to 12, the value of ay is equal to 0. So we have at this point when x equals to 12. So if we plot or if we connect the lines, now if we connect the coordinates, so we would have this influence line. So this would be the influence line for the reaction at A using static method. Now, what does it mean? If our live load is on the A, at point A, or at x equal to 0, this would give us a positive reaction. Okay? And if our live load here is at point C, okay, or at 4 meters from A, that means we do not have a reaction at A, since we have a 0 coordinate here. But if our live load is at point D, or at 8 meters from A, this would give us a negative reactions at point A, or a negative AY value. So that is the purpose of influence line. So it gives us the idea on the orientation or the value of our reaction as the load is moving across the beam. Okay? Now, again, this is for our first method, which is through statics. But what if we use the Muller-Breslau's principle? So in Muller-Breslau's principle, we will not be using this long solution. Okay? So the first step in drawing the influence line using Muller-Breslau's principle, we just need to eliminate the support at the point where we want to draw the influence line. Since we are asked to draw the influence line at reaction at A, so we just need to apply a load upward, and we need to create a deflection at A. Okay? So if we remove the support of at point A, there would be a deflection, or our point A moves upward, and this movement here is equal to the 1 unit load. So that means we have a movement here which is equal to 1. Now, our beam still remains rigid, so that means this would be the deflection of our beam if we move A upward. So this would be the new shape of our beam. Now, imagine if you eliminate the support at A and then you apply a load upward. So that means there would be a movement of that point. So there would be a movement, and that movement is equivalent to 1 unit deflection. Okay? And since our beam remains rigid, so that means this would be the qualitative deflection. Okay? So at point D, there would be a change in the direction. Since we have a support at point C and support at E, that means we don't have a movement at that specific point. So therefore, point C and point E is still on its original position. So there would be no movement. Again, C and E are restricted to move vertically. Okay? So as what you can see, so the deflection of our beam is similar to our influence line, correct? So that means at point A, so there's a movement of 1 coordinate. Okay? Then at point C, that's still 0. Okay? But at point D, we do not know yet what is the coordinate at this point. But we know that at point E, this is equal to 0. So how are we going to compute for the coordinate of the influence line at point D? So basically, we will just be using geometry here. So by ratio and proportion, now we know that this is 4 meters and this one is 4 meters. So by ratio and proportion, we have 1:4 equals to, let's say this is our y. So we have y:4. So that means y is equal to 1, correct? So y here is equal to 1. That is the coordinate at point D. So basically, we expedite the procedure on drawing the influence line. So that is the use, or that's the principle used by Muller-Breslau. So therefore, this is our influence line for the reaction at A, using method number 2, or the Muller-Breslau's principle. Now, for our second question is we should draw the influence line for our reaction at C. We may not solve for the reaction at C because we have solved it already na. So we know that when our x is equal to 0, we have already computed that our cy is equal to 0. When our x is equal to 4, we already know that cy is equal to 1, correct? And when our x is equal to 8, we know that Cy is equal to 2. So again, we have already computed the value of Cy during our computation for the influence line of the reaction at A. For our last situation, Cy here is equal to 0. So therefore, at x is equal to 12, Cy is automatically equal to 0. So we know again that when x equal to 0, the value of Cy is equal to 0. So therefore, at point A, so we have this Cy is equal to 0. Then when x is equal to 4, Cy is equal to 1, correct? So therefore, we draw here Cy is equal to 1. Then when x is equal to 8, we know that Cy is equal to 2. And for our x is equal to 12, Cy is equal to 0. So this would be the influence line for the reaction at C using static method. And as what you can see here, when our live load is at point D, okay, since we have influence line here, or we have coordinate here of 2, that means when our live load is at point D, that would give us the highest value of the reaction of our C. Okay? So that's how you read the influence line of the beam. Now, if we use the Muller-Breslau's principle in drawing the influence line of the reaction C, so again, we delete the reaction, or we delete the support at C, and then we apply a load upward. So that means there would be a movement of point C upward, and this movement is equivalent to 1 unit deflection. So our beam remains rigid, so we have A to C. So this would be the deflection of our beam. So again, if we delete the support at C, then we apply load upward. So we have our point C moved vertically at 1 unit deflection. Okay, and this is also our influence line. Okay, so by looking at the possible deflection of our beam when we apply load at C, this would give us the idea of the influence line, since again the deflection of our beam is similar to the possible influence line. Okay, so therefore the influence line would be like this, in which at A we have a 0 C, but at point C we have 1 unit. Okay, that is equivalent to 1 unit deflection. And then at point D, we do not have the value yet at this point, but we can solve that by using ratio and proportion. We know that this is 1, and the distance from C to A is 4, and distance from D to A is 8 meters, correct? So by ratio and proportion, we have y is to 8 equals to y 1 is to 4, and this give us y is equal to 2. So therefore, the value at point D, or the coordinate at point D, is 2. And the coordinate at point E is equal to 0, since we have a support at that point. So this is the influence line of our beam at support RC using the Muller-Breslau's principle. And in the second part of this discussion, we will solve question letter B and question letter C. So if you wish to continue the discussion, so the link has been posted in the description below. Thank you, but please don't forget to subscribe to my channel, and God bless.